All right, so in section 5.1, we talked about factoring, basically, right? Prime factorizations, in other words. And we looked at different ways to do divisibility, to decide if something was divisible by certain prime numbers, as well as some composite numbers. And what we're going to do in this section is we're going to actually look for greatest common factors and least common multiples. And the portion of this that we're going to do today is the greatest common factors part, okay? And then we'll do the least common multiples next time. Okay, so the first one that we're going to look at is the greatest common factors. The greatest common factor of a group of numbers, and we'll typically do either 2 or 3 numbers when I say group of numbers, but generally it could be used for any group of numbers, is the largest number that's a factor of all the numbers in the group. And it uses the word natural here just to indicate that you're not going to be dividing by any fractions or negatives or anything like that, but you probably assumed that part already. So we're looking for the largest number that divides all the numbers we're looking for, or we're looking at. Now we're going to learn 3 different ways to find greatest common factors, and they all have their own merits, okay? Now, in every bit as much as I just showed you 2 ways of doing prime factorization, and I said there's not going to be anything in your book that's going to ask you to do it in one way or another, that's not true for this, okay? You're actually going to practice at least 2 or 3 problems in each section for the different methods for doing them. And if you're asked on a test for that specific method, I expect to see that specific method. So it might be something when you get to a note card that you want to write down the difference between the methods or the descriptions. Now the descriptions are pretty descriptive. They really do indicate what you're supposed to do. So if you're being very cautious and careful about the descriptions, you shouldn't have too much of a trouble. So here's what I mean. So this first method is the prime factors method, okay? And the prime factors method, these are the steps to doing it. So the first thing you have to do is find the prime factorization for each number. Okay, so we did that for 300 on the board as our last problem, right? When I do 300 on the board, I found the prime factorization, and I can use whatever method I want to find that, okay? Find the prime factors. But I do it for however many numbers I'm working with. So if I do have 2 numbers, I do it for 2. If I have 3 numbers, I do it for all 3 of them. And then I look at what primes are common to all of the factorizations that I have. So in other words, if they're all divisible by 2, then 2 gets included. And I look for the least number of them. For instance, if the first value has 1 2 and the second value has 2 2s, well, they only have 1 2 in common, right? So it's the least exponent, the least number of these that they have in common. And then all of these common factors in these factorizations, we take the product of those, and that's my greatest common factor. This is probably the method that you have seen before. All right, so we're going to work with 2 numbers in this particular example, and we're going to use the prime factors method, which is the one that we just described. And we're looking to find the greatest common factor between 400 and 110, right? So you probably had no idea when I described it, I'm sure. No possible idea that I don't think in factor trees. That didn't come across at all, did it? I think, with that division algorithm. I know it's kind of a shock, but so I'm going to show you that as I'm working, and we're going to go from there. And so if you're not liking it, it's okay. You don't have to do this on your paper, but this is how I think. And so I'm going to model that for you so that you at least have some exposure to this, whether you think this way or not. It's good. All right, so 400, smallest number that divides 400 is 2. 400 divided by 2 is 200. Thank you. Smallest number that divides 200. 2. 200 divided by 2? 100. Smallest number that divides 100. 2. 100 divided by 2? 50. Smallest number that divides 50? 2. I get 25. Good. Now, how about this one? I can't do 2 anymore. 5. And I have 5 and 5, right? All right, so I'll write out what I have over here. I have 400. It is 2 to the how many? How many 2's do I have there? There are 4 of them. And then this is times 5 to the second. Thank you. So 400's prime factorization is 2 to the 4th times 5 squared. Okay? We're going to do the same thing for 110. Smallest number that divides 110. 2. And I divide it and I get 55. Smallest number that divides 55. That is 5. And I divide it and I get 11. So the number 110 is actually 2 times 5 times 11. Now I'm going to show what I'm about to show to you in 2 different ways. I'm going to show it to you from the division description over here on the left first. Okay. One way that you can look at this is you can simply pair up what they have matching. These 2's match, agreed? And then these 5's match, and that's it. Yeah? So if I think about it from over here, I can say the greatest common factor is 2 times 5, which is 10. 10. Yeah, it's not squared, it's times 5. Now, if I think about it from the perspective of having written out the prime factorizations, because that's actually how this slide is described, isn't it? It talks about the least exponent in factorizations and whatever. So if you get to the left-hand, or the right-hand side over here, one way to think about this then is to say, okay, well, they have a 2 in common. Yeah? And what is the least exponent on any of the 2's? It's a 1, because I don't have it written in here, but that's 2 to the 1. It's a 1. That's my least exponent on the 2's. And then I notice, oh, they both have, so they had a 2, they both have a 5. So I have a 5, and what is the least exponent on my 5's? It's a 1, and because this is 5 to the 1 right here. And then I have 2 to the 1 times 5 to the 1, and of course I still get 10. Okay? So you can go in the prime factorization with either of these approaches. So at the end, in other words, of doing all these divisions, you can simply pair them up. Okay? Just like I did, and you can call it good from there. That's fine. Or you can write them out like we did with their prime factorizations and then look for the common terms and the least exponent, and that's okay as well. Now, the reason, by and large, that I mentioned this exponent idea on the right-hand side is because when we get to least common multiples, it's going to come back up again, and it's going to make more sense when we get there as to why that's happening and why it's useful to think of it that way. Okay, is everybody good with that method? Prime factorizations, okay? Method number 2. And this one's a really nice one. You're probably going to like this one too. It's very clean. All right, so this one's called dividing by prime factors. Okay, so the description actually tells you what you do. All right, we're going to divide by prime factors. So the first thing you do is you write the numbers that you're trying to consider in this group on a row. That is, you write them beside each other with some space so it doesn't look like they run into each other, but you write them beside each other. You divide each of the numbers by a common prime factor. So you look for 2, you look for 3, you look for 5 or 7. Maybe you decide, oh, they both have an 11 in them. It doesn't matter the order. You don't have to go in order necessarily. But you're looking to see what prime numbers will divide both of them. Okay? So if you notice they're both divisible by 5 and you want to start there, that's great. You can start there. And then you divide those numbers by that value. and then you look at the quotients. That means the result of the division. Whatever you get as the answer on that division, you look at those numbers and you say, what numbers do those two numbers both divide by? You say, now I see it. They're also divisible by 3. I didn't see the 3 at first. I saw the 5 at first. Fine. I divide them both by 3. And we keep doing this process over and over again until we get down to some kind of quotients that do not have anything in common anymore. No more common factors. And then the greatest common factor will be all the numbers you divided by, which is the numbers you found in step 3. That should say step 3 at the bottom. My apologies. Not 2, 3. So you might notice on your sheet that I didn't leave very much space for this one. The nice thing about this one is that it doesn't take as much space as prime factorization. You just don't have to go as far because you're not dividing them all the way out to their fullest form. You're just dividing them in as far as they will divide by both values. So here's what we do. We take our 410 and our 360 and we write them beside each other. Again, not so close that they run into each other, but beside each other. And you will see that we are going to do this division algorithm with these. You could do 3 terms here too. It doesn't have to be 2. I could have 410, 360, and 150, and it would just be 3 of them all beside each other, okay? Now, what you are seeing, though, is actually the form that you have to use. This one doesn't work with trees. Like, I'm not actually finding the whole factorization, so I can't use a tree like that, okay? But what I'm looking at is I want to look at any prime number that you notice when you're looking at this that divides both of these numbers. So somebody give me one prime number that will divide both of these numbers. Jonathan says 2. Okay, so Jonathan says 2. So somebody tell me 410 divided by 2. 205. And then I need 360 divided by 2. 180. All right, so far so good? So I'm dividing them at the same time. That's something different. I need to do the same thing again. I say, 205 and 180, they still have something in common. 5. So I'm going to divide them now by 5. Okay, then what is 205 divided by 5? 41, that's right. And how about 180 divided by 5? 36. Thank you, Jessica. And at this point, I'm actually stuck because 41's prime. It doesn't divide by anything else. Okay? And 36 is not prime, but if 41 doesn't divide by anything, then I'm not going to be able to take 41 and 36 and divide them by the same value. Does that make sense? So I'm done. I don't have to do any more work. I don't have to find any more. Okay, I'm done. All I have to do is take a look at what I divided. I divided by 2 and 5. I think I need a little bit different color in this board. Let's go with the yellow. That'll work better. And the 2 numbers that I divide by are my greatest common factor after I multiply them by each other. So my greatest common factor is 2 times 5, and it happens to be 10. I promise the greatest common factor is not always 10. Okay, just was for the 2 examples I picked. So I kind of like this one. It's not very much work compared to the other one. I don't have to do near as much division. I don't have to do near as much comparison because the comparison is just right there on the left-hand side for me to see, right there. Okay. We okay with that one? We have one more, and it's a little bit weird. The last one we're going to do is the Euclidean algorithm. And I'm going to read this, and I'm going to let you write it down, and then the best way to describe it is going to be for me to show you when it's working, okay? So to find the greatest common factor, you divide the larger number by the smaller number. You take the remainder and the divisor, which is the number you divide by. And again, you divide the larger number divided by the smaller number. So never do I care what the quotient is. I don't ever care what the answer is when I do the division. All I care about is the remainder. Every time I take the remainder and the original number I divided by, and I divide again. And I keep doing this until I get no remainder. And once I get no remainder, then the last number that I divided by was my greatest common factor. All right, so we're going to work with the numbers 72 and 126. So what this says I'm going to do is I'm going to take the larger number and divide it by the smaller number. So this happens to go in one time. It's not real exciting, I get that, right? And I subtract. So this is kind of like back to when we were working with changing the bases, right? And we were working with you know, the Egyptian and Babylonian forms and whatever, okay? All right, so what's 126 minus 72? What is it? 54. So the values that are of concern to me right now are the remainder and the divisor. I do not care about the number 1, the quotient up at the top, at all. So I look at those two numbers, and I divide the larger number by the smaller number, which the smaller number has to be the remainder. Otherwise, you didn't divide by enough, okay? That's what it takes to be a remainder. It has to be smaller than the number you're dividing by. Everybody's with me on that, right? That's just a process that you did back in 4th grade, okay? All right, so we're going to take 54. It's going to go on the outside. The larger number, the divisor, is the 72, and we're going to do the same thing again. How many times will 54 go into 72? Just once, and then 1 times 54 is, of course, 54. It doesn't always give you 1 at the top, okay? That doesn't always happen. But what's 72 minus 54? That's 18. Again, the numbers I care about are the remainder and the divisor. So I take my remainder, and it will be dividing my divisor. How many times does 18 go into 54? That one's 3 times, and you guys can use calculators to do this, right? So what's 3 times 18 then? Somebody say it really loud. It's actually 54, right? This one actually goes in evenly, and I get 0 remainder. When I get 0 remainder here, that tells me I'm done. Okay? That's my indication that I'm done. So what is it, Tyler? 18 is the greatest common factor. The last number that we divide by is the answer. The process for doing this is really not that difficult. It's really weird looking, right? You have to remember what you're dividing by what, and you have to remember which pieces matter and which don't. But the process itself is not difficult. Yes, Mark?
Why would 3 not be 3?
It would be a common factor, but not the biggest one. Right? So you want the largest thing that will divide both numbers. 3 would be actually would be smallest. Would be the smallest? No, 2 would be the smallest. 2 will divide them both, 3 will divide them both, and so forth.
It'd be the least common multiple, right?
No.
No?
Least common multiples are larger than the numbers you're working with to begin with.
I thought 18 and 3, least common, the multiple of 18.
The 18 comes about as it is the product from the product of the factors that are in common. Yes. Yeah, so when we were looking at those previous methods and we were saying step 3 or 4 at the bottom, whatever the bottom one was, and it said take the product of the previous values, yes, 18 is coming about from that product of the previous values idea. Yeah. All right.